So let's look at some more basic sequences. I think geometric sequences overlap nicely with our introductory sequences, but also provide us with a couple more variables for us to get a handle with using in our programs. So, the important things to know about geometric sequences is that the geometric sequence has a first term as all sequences do, but this one is special. It's a first term and it's notated A, a first term A. So this will be the very first value of our sequence. Every time we see a first term A for our geometric sequence, that'll be the first term that our geometric sequence starts at. The second important value for defining a geometric sequence is R. Also, they have ratio R. A and R allows us, if we know A and R, then we can find any term in the sequence. Which is very useful. Right, nice property to have. So let's look at a few basic example geometric sequences. So I'm going to list my A values here, list my R values beside them. Then I'm going to place a line. I'm going to list all my A values again because I want to be in sequence. Let's go to A, R to the 4 over here. And then obviously it's a sequence, so it goes on forever. So our A value is 1 and our R value is 1. Well, then our initial term is obviously 1. And our second term is calculated by taking 1 and multiplying it by our R value, which is 1, which means we get 1, multiply it by 1 again, we get 1, multiply it by 1 again, we get 1, right? So each term is just calculated. A value is 1, R value is 1, A, 1 times 1, times 1 times 1 times 1 equals 1, right? And this will obviously continue forever. So we're just going to end up with infinite ones in this particular line. Now we can include a slightly more complicated equation. R is equal to 2. 1, 2. Because our first term is still the same. Our first term is A. Our first term is still the same, right? Our second term over here, so this is our first term, our second term, our third term. Our second term over here is A times R. 2 times 1 is 2. Our third term is A times R. 2 times 1 times R again, times 2 again, which is 2 times 2 is 4. Right? And we continue doing this for our fourth, our fifth, all the way on to our infinite numbers of terms, if we had that time. 8 and then 16. We can do different R's. This negative R creates this interesting behavior where we oscillate between negative and positive numbers, and it should be relatively easy to see how we could change that behavior so that we had the same sequence, but the 1s and the 9s were negative, etc., and the 3s and the 27s, etc., are all positive. That should be a nice simple transformation for you to figure out. 2 and 3, this is the first time we're messing with our first sequence. We'll see that this creates actually quite a predictable impact. 2, 6, 18, 54. We're just doubling each of our previous sequence. We'll see that if this was just a regular 1-3 sequence, our 2-3 sequence would just be double it, right? So our 6 here, we have our 18 here, 9 times 2 is 18, 27 times 2 is 54, 81 times 2 is 162, etc., etc. These guys are a little more complicated. Here we're starting at 27 and we're moving by 1 over 3. This is actually going to create a diminishing sequence. 27, 9, 3, 1, 1 over 3, and down and down and down. We can do funky things like have a negative fraction as well. But all we're doing is plugging in for A and R squared, right? So here we just, to get 3 over 4, all we have to do is square our value, which is 1 over 4, because negative 1 over 2 squared is 1 over 4, multiplied by 3 is 3 over 4. Piece of cake, right? Each value is really easy, really straightforward to find, and this is calculated in very similar ways to all the graphs that we looked at, to all the charts groups that we've looked at. We've done an awful lot of this sort of thing. It's a very similar action. Negative 3 over Sorry, it's not negative 3 over. I missed a value. 3 over 4, negative 3 over 8, 3 over 16. That's my fault. So, how do we generate code for all this? Unfortunately, I can't show you all the code that we can use to generate these, as my students fully well know. But I can give you some basic hints, some basic tips, and I can point out that if we look back at our introductory sequences, this sequence here and this sequence here look mighty familiar. 1, 2, 4, 8, 16. 1, 2, 4, 8, 16. 1, 1, 1, 1, 1, 1, 1, 1. Oh, that's very interesting. So, how did we generate those previous sequences? Well, last time, if you remember, we did something slightly wrong, and we're going to fix that right now. So, in this case, if we set our x value not to 1 but to 0, for geometric sequences, this gets us our first term. This is why we were getting our second term accidentally in this particular case. For geometric sequences, 0 gets us our first term. This is also one of the reasons why computers will quite often count from 0, because in a lot of cases this is very useful. So it's very, very desirable behavior. X equals 0, and obviously if you just want 1, then you just add 1. While true, this keeps our while loop running forever, of course. We're going to print that exact same value of x that got us most of the way previously, which was 1 star star x. This value gets us our list of 1s all the way at the top here. We can follow this up with 2 star star x. So the important bit here for you as a student is to understand how we're going to move this piece of math and this piece of code together to create something that's useful to us. So we've gone 1 star star x. This particular one generates a bunch of 1s and doesn't tell us very much. But this one has changed a value, and the value that's changed is this value. And because this value has changed to 2, and this is where our 2 is, maybe this is our R value, right? Maybe this is our R value. Okay, let's keep generating some code. Our third sequence here is generated by using negative 3 in brackets. And you can generate this however you like. This is just one of the most efficient ways that I figured out that also sort of fits in with what we've been doing so far. So here we again are putting our exponent to x, but it's negative 3 in brackets. Now it has to be in brackets in order to make sure we get the right behavior for our negative. Again, this is looking awful lot like R. Right? We're starting to confirm our suspicions. And if we plug this into the computer, you will actually find that it generates our desired sequence. Next, how many more am I going to give you? I'll give you one more. The kindness of my heart. So next up, we're going to look at how A changes things. Well, if we look at it, we can see that A just multiplies our entire previous sequence by the A value. So that makes things a little more straightforward, right? We can just preserve that in the math. We multiply our entire generation by the A value. Our A value is 2, so we're going to multiply it all by 2, right? And then the entire value for 1, 3 would just be, well, that would just be a 3 value here, right? Right? Asterisk, asterisk, x, close bracket. And I'm going to end my print statement here, though we'll note that this only gets us 1, 2, 3, 4, our first 4, which means you should do these for an exercise. So this is a nice, simple little piece of code that, as long as I make sure to finish my loop, generates out each of these first 4 sequences. It's just based off of this initial piece of code, right, that gets us into an infinite loop in the first place. And then from there, we can make slight modifications to how we see the output of that code, and we get all of these different interesting sequences, all of which have different interesting properties. Right. So a quick example, the output is all listed right here, but the computer is obviously not going to put it into that nice of a chart. We'll talk about more how to do that as time goes by. In general, this chunk of code's output is then going to look... Oh, what's it going to look like? It's going to obviously be this whole chart rotated. So we'll start with our ANR value 1 over here on the left. We'll follow on to our second one, 1. Our third one, 1. Then we'll be followed by a 2. So it's just going to be a reflection of this chart like this. 1, 2, -3, 6, 1, 4, 9, 18, 1, 8, -20, -27. 54, etc., etc., etc. Because these numbers actually get quite large different speeds, then we see quite a sort of triangular pattern developing in the output, which you will see if you actually run it on a computer. So that's geometric sequences. We're going to keep on manipulating sequences, but our real goal is to get us functions that can pass useful information to other parts of our programs. So that means that we can't have sections of our program just running forever. So our next big step is going to be placing limits on these sequences.